Grounding grid calculations are crucial for ensuring safety and proper operation in electrical systems, particularly when dealing with transformers. Several resources provide detailed information and methodologies for these calculations. Firstly, IEEE Standard 2013 titled Guide for Safety in AC Substation Grounding offers comprehensive guidelines and practices for designing grounding systems in alternating current substations. This standard covers various aspects of grounding, including soil resistivity measurements, touch and step potential calculations, and the design of grounding grids to limit these potentials to safe levels. Secondly, IEEE Standard 142-2007, known as the IEEE Recommended Practice for Grounding of Industrial and Commercial Power Systems, provides recommendations for grounding electrical systems in industrial and commercial facilities. This standard, often referred to as the Green Book, covers topics such as equipment grounding, neutral grounding, and the bonding of electrical systems to minimize the risk of electrical shock and equipment damage. Thirdly, the book Neutral Grounding in Electrical Distribution Systems Theory and Practice by Theodore M. Bergman is a valuable resource for understanding the principles and practices of neutral grounding. This book covers various grounding techniques and their applications in electrical distribution systems. In calculating a grounding grid for a 150 kVA, 13,200/220/127 volts transformer, several key factors must be taken into consideration. These factors include soil resistivity, transformer fault current, fault duration, target ground resistance, and grid geometry. Let's delve into each of these factors in more detail. Soil resistivity refers to the resistance of the soil to the flow of electrical current. It is a critical parameter in grounding grid design because it affects the ability of the grid to dissipate fault current into the earth. Soil resistivity varies depending on the type of soil, moisture content, temperature, and the presence of dissolved salts. It is typically measured using methods such as the Wiener 4-point method or the Schlumberger method. Accurate measurement of soil resistivity is essential for proper grounding grid design. Transformer fault current is the maximum current that can flow through the grounding grid during a fault condition. It depends on the transformer's impedance, the system voltage, and the fault impedance. The grounding grid must be designed to safely carry this fault current without exceeding the allowable temperature rise of the grounding conductors or creating hazardous touch and step potentials. Fault duration refers to the length of time that the fault current flows through the grounding grid. It depends on the protective devices in the electrical system, such as circuit breakers and fuses, and their operating time. The grounding grid must be designed to withstand the thermal and mechanical stresses caused by the fault current during the fault duration. Target ground resistance is the maximum allowable resistance between the grounding grid and the earth. It is typically specified by regulatory codes or standards such as the National Electrical Code, NEC, or IEEE standards. The target ground resistance is chosen to ensure that the grounding grid can effectively dissipate fault current and limit touch and step potentials to safe levels. Grid geometry refers to the size, shape, and configuration of the grounding grid. It includes the number, spacing, and depth of the grounding electrodes, as well as the size and arrangement of the grounding conductors. The grid geometry must be designed to achieve the target ground resistance and to minimize touch and step potentials. After determining these factors, you can use formulas and methods from IEEE standards or the recommended book to calculate the required number and spacing of grounding electrodes. Let's talk about these one by one. Grounding electrodes are conductive rods, plates, or meshes that are buried in the earth and connected to the grounding grid. They provide a low resistance path for fault current to flow into the earth. The number and spacing of grounding electrodes depend on the soil resistivity, the target ground resistance, and the grid geometry. The formulas for calculating the number and spacing of grounding electrodes can be found in IEEE Standard 80 and other grounding design guides. Firstly, determine the soil resistivity using a soil resistivity test. This will provide the value in ohms meter needed for the calculations. Secondly, determine the maximum ground fault current that the grounding system will need to handle. This information can be obtained from the transformer specifications and the electrical system design. Thirdly, establish the maximum tolerable ground resistance for the grounding system. This value is typically specified by local regulations or industry standards. Fourthly, select the type of grounding electrode to be used, such as ground rods, ground plates, or ground grids. Each type has its own characteristics and suitability for different soil conditions. Fifthly, use appropriate formulas and software tools, such as those provided in IEEE Standard 80, to calculate the required number, spacing, and depth of grounding electrodes. These calculations take into account the soil resistivity, fault current, target ground resistance, and electrode type. Sixthly, design the layout of the grounding grid, considering factors such as the available space, equipment location, and potential hazards. The grid should provide a low impedance path for fault current to flow to ground. Seventhly, select the appropriate size and type of grounding conductors to connect the grounding electrodes and equipment to the grounding grid. The conductors must be capable of withstanding the maximum fault current without overheating or causing excessive voltage drop. Eighthly, consider the use of equipotential bonding to minimize voltage differences between different parts of the grounding system. This can be achieved by connecting all metallic objects in the vicinity of the grounding grid to the grid itself. Ninthly, perform regular inspections and testing of the grounding system to ensure its effectiveness and compliance with applicable standards. This includes measuring the ground resistance and checking the integrity of the grounding connections. Tenthly, document all aspects of the grounding system design, installation, and testing for future reference and maintenance purposes. This documentation should include drawings, calculations, test results, and maintenance records. In addition to these considerations, it is important to follow the guidelines and recommendations provided in IEEE Standard 80 and other relevant standards and codes. These standards provide detailed information on grounding system design, installation, and testing, and can help ensure the safety and reliability of the electrical system. For a 150 kVA 13,200/220/127 volts transformer, this involves determining the fault current, soil resistivity, and desired ground resistance to calculate the grounding grid specifications. Soil resistivity measurements guide the design, while fault current determines the capacity needed. The grid's layout impacts ground resistance and safety. Let's look at what the formula for calculating the grounding grid resistance entails. The grounding grid resistance, often denoted as RG, is a critical parameter in the design of grounding systems. It represents the overall resistance of the grounding grid to the flow of fault current into the earth. The formula for calculating the grounding grid resistance can vary depending on the specific configuration of the grid and the soil conditions. However, a commonly used formula is based on the assumption of a uniformly distributed grid in a homogeneous soil. The formula is Rg equals ρ divided by the square root of A plus the soil resistivity divided by L, where Rg is the grounding grid resistance in ohms. ρ is the soil resistivity in ohm meters. A is the area occupied by the grounding grid in square meters. L is the total length of the grounding conductors in the grounding grid in meters. This formula provides an approximation of the grounding grid resistance based on the assumption of a uniformly distributed grid in a homogeneous soil. However, in practice, soil conditions may not be uniform and the grid configuration may not be perfectly distributed. In such cases, more complex calculations or computer simulations may be required to accurately determine the grounding grid resistance. Some of the additional considerations for grounding grid calculations are soil resistivity variations with depth or location, non-uniform grid configurations, the presence of buried metallic structures, frequency dependence of soil impedance, and the effects of temperature and moisture content. Let's explore each of these considerations more fully. Firstly, soil resistivity variations with depth or location are prevalent, therefore soil resistivity can vary significantly with depth and location, especially in areas with layered soil structures or varying moisture content. These variations can affect the current distribution in the grounding grid and the overall grounding resistance. In such cases, it is necessary to perform soil resistivity measurements at multiple depths and locations to obtain a more accurate representation of the soil conditions. Secondly, non-uniform grid configurations require non-uniform grounding grid configurations, such as irregularly shaped grids or grids with uneven electrode spacing, which can affect the current distribution and grounding resistance. In these situations, it is necessary to use more advanced calculation methods or computer simulations to accurately determine the grounding grid resistance. Thirdly, the presence of buried metallic structures, such as pipelines or underground utilities, can influence the current distribution in the grounding grid and the overall grounding resistance. These structures can act as additional grounding electrodes or provide alternative paths for fault current to flow. Fourthly, the frequency dependence of soil impedance is applicable in many situations. Soil impedance can vary with frequency, especially at higher frequencies. This variation can affect the performance of the grounding grid under transient conditions, such as lightning strikes or switching surges. Fifthly, the effects of temperature and moisture content on the soil should be considered. Soil resistivity is influenced by temperature and moisture content, which can change seasonally or due to weather conditions. These changes can affect the grounding grid resistance and the overall performance of the grounding system. To account for these variations, it is necessary to perform soil resistivity measurements under different temperature and moisture conditions. When performing grounding grid calculations, it is important to use appropriate software tools to aid in the design and analysis process. These tools can help simplify the calculations, visualize the results, and optimize the grid configuration for various soil conditions and fault scenarios. Some popular software tools for grounding grid design include ETAP, SIME, and Safe Engineering Services and Technologies, SES, CDEGS. ETAP, Electrical Transient Analyzer Program, is a widely used power system analysis software that includes modules for grounding grid design and analysis. It allows users to model complex grounding grid configurations, simulate fault conditions, and calculate touch and step potentials. SIME is another power system analysis software that offers a grounding grid design module. It provides tools for soil resistivity analysis, grid impedance calculation, and touch and step potential assessment. SES, Safe Engineering Services and Technologies, CDEGS, current distribution, electromagnetic fields, grounding, and soil structure analysis, is a specialized software package for grounding, electromagnetic interference, and electromagnetic transients analysis. It offers advanced modeling capabilities for complex grounding grid configurations and soil structures. These software tools can help electrical engineers and designers to efficiently design and analyze grounding grids, ensuring the safety and reliability of electrical systems. Grounding grid calculations involve considering factors like soil resistivity, fault current, and grid geometry. The aim is to design a system that safely dissipates fault current, protecting equipment and personnel.